In this tutorial, we'll be discussing cyclohexane, which is a 6-membered ring, and it's very stable. If we look here at our planar structure, we don't have perfect bond angles because it's planar, but cyclohexane is able to achieve perfect bond angles if it puckers a little bit, and we can see here, if we pucker it a little, we have staggered bonds and no longer eclipsed bonds. One thing to keep in mind is that we also have another 6-membered structure called benzene. It is not the same as cyclohexane because this is sp2 hybridized instead of being sp3 hybridized. So keep that in mind, don't get confused by that. Let's examine one of the two major conformations of cyclohexane. Here we have what we call the boat structure. If we take a look here, we have our groups placed in different colors for illustration. And we can see here, if we look down this plane, that we have completely eclipsed bonds here and here. And if we turn it this way, we can see the boat structure we have here. And we have some interaction between these two atoms at the top that we call flagpole interactions. This becomes important because if we were to have, for instance, methyl groups or something even larger than that, we would have lots of hindrance here because of those interactions. Now let's take a look at the other conformation, the chair conformation, which is indeed more stable than the boat that we just took a look at. If we see here, this is our chair conformation that we have. We have perfect sp3 bond angles because we're in the chair conformation, which is stable. If you take a look at these bonds here, they're completely staggered all the way around, which relieves our torsional strain. There are two different orientations that our bonds can be in. If we see here, our atoms are all up and down. They're in the axial position. They're perpendicular with reference to the plane of the molecule. And we notice that they're alternating all the way around. Here we have down, we have up, we have down, and we have up. In comparison, we can have equatorial, which the way I remember is equator goes around the Earth. And so these are our equatorial bonds. They're also going up and down all the way around, but they're not going to be in the same position as our axial was. We see here that we don't have any torsional strain once again because we have staggered bonds, as you can see, and because it's in the chair conformation, then we don't have any angle strain either. So here we have a cyclohexane in our chair conformation, and we see that all of these atoms are in the equatorial position. One thing to note is that when we have large substituents, we want to have them in the equatorial position because that will keep them away from the ring, away from the other groups, and that will relieve some of the strain and the steric hindrance, the crowding. So there is a way that we can change the equatorial to the axial, move from one chair conformation to the other, and the way we do that is a ring flip. Now, when we say ring flip, we're not talking about just turning it over like this, because if we just turned it over, we still have everything in the equatorial position. So the way that we do the ring flip is we take one side and we move it up. Now, do you see when we move that up, we're actually now at our boat conformation again. You see how we have the eclipsed bonds here on each side, and we have the flagpole interactions that we discussed earlier. So now what we do is we take the other side and we move that down. So now we notice we have everything in the axial position when it was in the equatorial earlier. So if we compare our axial that we have before, we see that they're the same. Now let's take a look at cis and trans for our chair conformation for cyclohexane. Here we're going to be illustrating with our two red atoms. We see that in reference to the molecule, the plane, we have two above, and so this is going to be our cis. So if we use this as our example here, if we compare all the way around, as long as they are above the plane of the molecule, they will be cis. So here we have cis compared here. Here is cis again. These are cis, and these are also cis. Now if we use another that we've built, we can illustrate our trans. Here we have the red above the plane, and we have the red below the plane. Now if we use this again as our example, this is up, this one's down, therefore trans, this one's down, therefore trans, and this one's down, and so forth. It doesn't matter whether you have the axial or the equatorial position, as long as the two are above the plane, then they're going to be cis, and if one's above the plane and one's below, then they will be trans.